We will now look at the second part of the in-class exercise. So here we have 4 different functions fn. So they are, you can imagine that they can be the count of different algorithm. We want to convert that into big O. So as mentioned before, I think the critical thing over here is to recognize the order in which different terms represent. You want to eliminate all those different lower order items, and also eliminate the constant coefficient. And that will be your way of writing the final big O representation. Here we look at the first one. You have n cube, n square, and then n, right? So, I mean, this is the example we have talked about in the lecture slides. Although all of them are in polynomial class, but if you plot out their value or you just use the Excel spreadsheet to try out their value on different ends, you will see that n cube will dominate n square, and you will also dominate n. And of course, you will dominate the constant term, which doesn't respond to the increase in n value at all. And when you write the final statement again, the 3 over here is redundant. You can drop it. So you will write only n cube. All right, so I think this is the first part. The second part, again, we have compared this function in the class exercise already. We compare n square against a log n. And of course, we already know that n square also dominates the linear term n, right? So you can eliminate both. In the end, you only have n squared, right? So it's going to be big O n squared. Right, so this one might not be so straightforward to compare in the first sight. And even in the case that you put both terms in the Excel spreadsheet, you might see that 9 times n seems to be larger than n times log n for like very large n's. But one thing to recognize, or to potentially help you to determine which one is dominating, is to compare 9 against log n, right? Because n are all the same, right? So what really matters is the term that's being multiplied to n. So if you write it on the side, you have log n, you have 9. 9 stay the same, right? No matter how you change your n value, 9 will always be 9. But as n grow larger and larger, for example, eventually you can try something that's really large, let's say 10 to the power 100. Then even you have a log n with 10 as the base, you have 100, right? While 9 is still 9. So that's why you see that in the limit, remember, big O notation is really about going to the limit, right? In the limit, 9n will be dominated, right? So as a result, you will have n log n as your big O, a big O notation. Okay, the final part, yeah, we have seen this as well in class. You have two classes, two category of the count, 2 to a power of n. This is exponential, growing very, very fast, and n squared, right? So you drop n squared, then you have 2 to a power of n. Okay, so this is the first part on converting the regular function into a big O notation. If you need more practice, make sure that you actually try out the practice that's in the tutorial question. We have a lot of function for you to do the conversion. Right, the second part is the analysis. So these are the counts that we derive in the very first part when we try to finish the first part of the in-class exercise. So if you look at the total count, right? So in this case, in the worst case, right, this 10 again over here is at most, right? But since we care about the worst case analysis, this is okay. You know? So you have in the worst case at most 19. And as you can see, there's no n in it. And this is not surprising, right? Because you are only checking for the maximum element for the first 10 numbers, which means that regardless how large your n is, your n can be 1 billion, doesn't matter, still only the first 10 numbers will be checked, right? So if you want to turn this count over here into big O notation, it's going to be big O 1. indicating that this is a constant time algorithm. And then the second part, you see there's a lot of n's, right? But what we really care about is the total count. Again, over here, this is in the worst case, right? You have, I mean, we can just put on a note, this is n most. You have 2n times n minus 1 plus 2. In order to do the simplification, you can actually just multiply everything out, right? So this is effectively 2n squared minus 2n plus 2, right? So just like the previous question, so you have three categories, n squared, linear term, and constant term. This two term will get eliminated. You drop the constant term, so your big O notation as a result will be n squared. Okay, so these two are the demonstration about how you can go from the algorithm, analysis of the algorithm, the count of operation, and finally the big O notation that completes your complexity analysis. The last part, right, this is where no algorithm get proposed, right? But you want to analyze the complexity of this problem. So you need to understand, like, given this problem, suppose you want to solve it. If you don't want to propose any algorithm, you can imagine that if you want to evaluate all the possible cases by pure elimination, or sometimes we call it brute force, how many operations are required? You have n students. You want to find 3 students with different last name. So in the worst case, if you want to do the pure elimination, you're going to find all the possible ways where you can assemble, you can pick 3 students, right? And then for each and every pair, or for each and every group of 3 students that you have picked, you will check their last name, right? Here we didn't say how many that you need to find. So the moment you identify the first group of 3 students with different last name, you are done, right? But again, you don't know, as the best case scenario, you don't know when the best case will happen. So you look at the worst case, assuming that the group, if it ever exists, will only be identified when you evaluated the last group in a class. So out of n students, the order is not important. You're going to choose 3 from them. Right, so again, you cannot stop here because you are interested in complexity. So you have to come up with the formula for that. So n choose 3. If you write it down as a formula, is n times n minus 1 times n minus 2. But you have to divide 3 factorial, which is 6. Right? So in other words, you can see that you can kind of simplify that, right? Is n squared minus 3n plus 2. Finally, you multiply the n into it. It's going to be n cubed minus 3n squared plus 2n. Right? So again, over here, you see that there are 3 separate terms, and then in increasing order. Linear, square, and the only one that's going to survive the domination will be n cubed. 1 over 6, this is a coefficient, not important. So when you write the big O notation, it's going to be big O n cubed.